Today, I'm joined by Ankush Halba, a doctoral fellow at Indian Institute of Technology, Roorkee. Ankush's work sits at the intersection of biomass to energy, waste to energy, life cycle assessment, techno-economic analysis, and real-world sustainability trade-offs. In this conversation, we are going to focus less on theory and more on what actually works, what breaks down in practice, and where expectations around bioenergy and circular economy often diverge from reality. Ankush, thank you for joining me today.
A warm greetings to everyone. Thank you, Carol, for having me in this podcast and for the kind introduction. I really look forward to our conversation, and it's a pleasure to be here.
Thank you so much. So, to break the ice, let's start with the first question. I wanted to talk about background and motivation behind your work. So, as I mentioned, you work across biomass to energy, waste to energy, and LCA, which is life cycle assessment, and also techno-economic assessment. So, what originally pulled you into this space? And if you could tell us, what problem are you actually trying to solve with your research?
Sure, I will go ahead with my background first, then we'll delve into the research problems. So, basically, I am an agriculture engineer by profession. So, I did BTech in agriculture engineering from State University here. So, during this curriculum, I was exposed to some field visits, so where I observed enormous amount of biomass waste, either which is burned or landfill. So creating an environmental burden to our ecosystem. So that's motivated me into delve into the biomass aspect. So I look out the waste to convert this type of waste like biomass waste or generally MSW waste into the energy. So after that, following these things, I joined masters in farm machinery and power. So where I learned about the farm machineries like rotavator, harvester, and many things, and the power which can fuel them. So where I did project on biodiesel and IC engines. So that helped me a lot to understand about the biomass to energy pathways. So in during the masters, I did a project on modification of biodiesel in IC engine for the stationary engine. So the results was quite good. So it was only a 1 year project. So I was expected to explore many pathways. So I joined a PhD in renewable energy in the same in another institute, IIT Roorkee. So where I explored biomass gasification, where biomass can be converted into a gas via process gasification, as the name suggests, where we are converting biomass into a combustible gas that can be used in the internal combustion engine coupled with alternator to produce electricity. It also has a byproduct like biochar, generally known as carbon-rich residues, which can be used as various purposes like water purification, as well as soil amendment and the carbon sequestration. It has potential to remove carbon from the atmosphere.
Thank you very much for that explanation. I think it will help to set the context because many people see bioenergy, at least that was my case in the past, as a single solution, while in practice, I think it's a bundle of very different systems, right?
Yes, we can say that it's a very complex system because whenever we talk about the renewable energy, either it's a solar, wind, or biomass power, they all have their pro and cons. Just like the solar, we cannot have the solar flux all the time and everywhere. Just like the wind, whenever we have the wind velocity, enough velocity to run the wind turbine, then we will have the electricity. Or in the biomass, we have the seasonal availability of biomass.
Got it. And now I would like to ask you about biomass versus waste to energy. So obviously it's not the same thing, at least I assume so. So biomass to energy and waste to energy I often group together. But from a technical and environmental perspective, could you tell us where do they meaningfully differ and where do people oversimplify?
Yes, that's a very interesting question. So, if we look out about the biomass, so we can say that biomass is the organism like dead plants, animal extractor, that was once recently lived instead of coal that has been dead for million of years. If we talk about the waste, it can be municipal solid waste, industrial waste, or any other waste. So whenever we are converting the combustible portion of waste from the municipal waste or any other waste into the energy, it is termed as waste to energy. There are other options to extract metals and other things from the waste that can be termed as e-waste. Or also there is a okay, sir. Also there is one thing when we deal about the biomass, it is available seasonal, but when we talk about the municipal solid waste, it can vary from city to city or day to day. And earlier I was asked to give some context about the life cycle assessment and techno-economic assessment as well. So basically, when we talk about the life cycle assessment, we can understand it by the birth and death concept. So basically, here we are saying life cycle assessment. That means we are sorry, pardon. So
It's okay.
we are accessing the things in terms of life cycle. So once we talk about the life cycle assessment, we can say that it's a potential environmental impacts of any process or any product that may be released into the atmosphere, and what are the environmental degradation consequences about that process or product. It has the various entities like start with the goal and scope, then we have to build inventory. After that, third process is called the impact assessment, and it is synchronized with the interpretation. Here we have the various functional unit. Either we can count the emissions, or there are 15 midpoint categories and 3 endpoint categories. Midpoint categories term as the early stages emissions or environmental degradation process, like climate change, acidification, and many other things. But end use endpoints are the points where we are accessing the total damage at the end, just like ecosystem, resources, and human health. And once we
Got it.
talk about the techno-economic assessment, it is generally termed as accessing the bankability of any project, because if we do not having any revenue from the project, we will not invest any money into these type of projects. So we generally make assumptions and check whether the project is economic feasible or not. So there are two. So these two are the pillars of the sustainability. So once we talk about the sustainability, we need to understand its ability to sustain anything over a period of time without compromising the need of future generation for their own needs in the future. So it has one pillar of environmental, second one is the technical, second one is the economical, and third one is the social aspects. So in the intersection of these points, it is called the sustainability. That is economic viable, social viable, as well as the economic.
Thank you very much for this clear distinction. Now, I guess everyone can agree that these are not the same things. And this distinction matters a lot, I would say, for policy, financing, and public perception. It's very important. Now, let's talk about the LCA, Life Cycle Assessment Reality Check. So, when you run full life cycle assessments, let's say, on these systems, what tends to surprise people most? Especially when it comes to policymakers, investors who assume bioenergy is automatically green.
If we do not understand how the life cycle assessment works, we can get confused, because it depends on the first one is the functional unit. In energy terms, we are generally have one unit of electricity production. So whatever the environmental impacts, they can be measured in terms of unit of electricity, and they can vary by the system boundaries. So there are different type of system boundaries. First one is start with the cradle to gate. That means the raw extraction of any material. then manufacturing process, then use it, and in the production phase once it exits from the factory. Another one is the gate to gate, where one material is entering into the factory and exiting from another gate. That is the second type of material. And third one is the cradle to grave, where we are utilizing all the product and dispose it. And last one is the cradle to cradle, once it is disposed in the earlier process and it is regenerating again. So if we talk about this into the birth and death sentence, if birth is cradle and grave is death, and again if we are taking the rebirth, then it will become the cradle to cradle. So sometimes the people only report the environmental impacts of gate to gate. So it might get confused because it does not account any supply chain emissions and any other emission. In the LCA, we totally account the emissions which is comes under the system boundary. And after conducting this assessment, we will divide into the scope 1, scope 2, scope 3 emissions. So both are equally important. If we talk about the researcher point of view, I am more interested in the whole environmental impacts. And if I am industry guy, so I would be more interested in the scope 1, scope 2, scope 3 emissions, because I have to meet the environmental compliance of the local government or the international protocols.
I also wanted to ask you when bioenergy actually makes sense in your view, because based on your research, in what specific conditions, if you could tell us, does biomass or waste to energy genuinely make sense, technically, economically, and environmentally?
So in my research, I used a model that is called 3P or 4P model. That is the public-private partnership, or 3P. And another one is the public-private people partnership, where we can say that the local communities will support us by providing land or taking a part in the operational supply chain, like supplying the biomass and the working as a supervisor, and for the many other and they can be available for the many other operations. uh, and the private entities, the firm, they will supply the technology and will take care of the plant throughout the whole life. And for the for the government side, they will participate as a providing the subsidies, incentives, and many other things. This type of systems in particularly current scenario will work for the especially for the developing countries, because the high capex capital expenditure is the major problem with the renewable energy systems. Either it will be a solar or wind. So that kind of system can be initially used to in the transition phase. Afterwards, once it's economic viable, environmental viable, and social viable, then we can go for the 100% renewable energy integration.
This is great because this is where we move from ideology to decision making. And also, let's talk about when it doesn't work. Because on the flip side, where do these systems, in your view, fail or become questionable? Let's say either economically or from a sustainability standpoint.
I will give you example of biogas plant. You have might heard about it. Biogas plant where we are creating the biogas from the biomass. So each process has their pro and cons. If we take the anaerobic digestion, so where we have uh, to need a great amount of moisture to make a slurry to put in the digester, and after a sustainable amount of time, it will produce a methane gas. That is a combustible gas, either can be used as a CBG, compressed biogas, or it can be used in the CHP plant, combined heat and power plant. But this is generally we are talking about the plant phase. If we don't have a reliable supply chain, like from where the biomass feedstock is coming to the plant, and what are the constraints related to the transportation, collection efficiency. If we do not cope up with these things, the plant might get stopped during its operational hour. Second thing is that we cannot run these plants throughout the year, because the capacity utilization factor, that is a ratio between the actual power generated by a plant to the maximum possible power generation. It is generally low for the bioenergy pathways, like 40 to 60%. There might be a various challenges to contribute this low capacity utilization factor. So in these scenario, the things will not work. Also in the developing countries like USA and many developed countries, they have a robust mechanism and they have a good investor. Also, they have a reliable market to generate revenue, reliable supply chain. But in the developing countries, it is currently in developing stage. Also, the recent trends in the carbon credit market, they can enhance their financial feasibility. In my last study, I did some carbon credit calculations. So where I found out, if I do not have any subsidies or carbon credit benefits, so my internal rate of return was coming around 86%. Once I utilize the capital subsidies provided by the local government as well as the carbon credit benefits, it's come down to the around 18%.
That's interesting. And could you also explain why those power plants cannot run around the clock full year?
Because right now there are various challenges with the plants. Sometimes there is some interruption or the unforeseen events, so we cannot run a plant 365 days in a year. So we have to put.
Oh, okay. So it's more about unforeseen events. It's not like from a technical standpoint, it's not feasible or possible,
No, right now
if
the
I
technol
understand correctly.
right now the techno tech matlab tech these type of technologies comes around the technology readiness level 8, where we can deploy technology into the ground. The more challenges are coming from the supply chain part and operational parts.
Mhm. I get it. Thank you so much. So now let's move to supply chains and GIS modeling, because you work with GIAs, which is Geographic Information System, GIS-based biomass supply chain modeling. So from your experience, how critical is feedstock logistics in determining whether a project succeeds or fails?
Well, that's a very critical questions, because once we talk about the scope 1, scope 2, scope 3 emissions, scope 1 is coming from the emissions coming from directly from the plant. Like if we talk about the bioenergy plant, so whatever the emissions it is creating in various process, it can be considered as scope 1. But when we talk about the scope 2 emissions, it is coming from the indirect things like purchasing the electricity, heat or steam. And once we talk about the scope 3 emissions, that are the emissions coming from the supply chain emissions. And the previous study reveals that, so the scope 3 emissions can be 70 to 90% of the total supply chain if we sum up the scope 1, scope 2, and scope 3 emissions. So here we need to optimize the supply chain, because if we are putting a plant which can save 100 kg of CO2 emissions, and in the supply chain we are emitting more than 200 kg of CO2 emissions, so there is no need to employ that plant, because ultimately we are creating more pollution rather than saving the
Mm,
emissions. So that's a
exactly.
major chunk of supply chain. And once we use the GIS or digital twin, that means GIS is something like the Google map, where we can access where the biomass is coming from the field, and where we have the road network. Also, there are some geological constraints in my studies. So I am conducting a study in the Indian Himalaya region. So this region is has the geological constraint, because it contains a very steep slope. So I have to model GIS for the manual collection, where the local people can collect the pine needles. Pine needles are the leaves of pine tree. They've fallen every year during the summer season. So the local people will go up to the 3 to 4 kilometer distance by walk. So they will go there and collect the pine needles because the any other collection method is not possible. So I always say the any renewable energy is a region specific study where we need to gather the data related to region wise, and we need to discuss all the things with the various stakeholders of this any project related to uh, the renewable energy. In my case, bioenergy, I talked a lot with local people, farmers, industry experts, investors. So that's why I got the idea and I include these aspects into my studies. So GIS really helped me to access the manual connection feasibility. And also I conducted a loss, accessibility loss. How much there are accessibility loss to collect the pine needles. Suppose we are reporting the 100 kg of pine needles. But when I conducted these studies, so I found out around 60% of loss are coming from the accessibility losses. So only I am getting the 40 kg of pine needle in the upstream supply chain. That accounts for all the manual collection and transportation, loading, unloading, pre-processing pathways, and then the plant utility. It is really huge, around 60% biomass you are losing in supply chain. But these ratio will be vary from the biomass to biomass, region to region, and the season to season. So here I use GIS for the spatial analysis, where I can where I have the supply points. Supply points means where I can collect the pine needles. After that, I model it to find out where I can place the intermediate storage options. Then where we can have a plant within the specific distance, because if we are transporting the biomass more than 100 kilometer transportation distance, it will cost me more, and also I am not saving any emission during my any bioenergy project. So that's a very critical to deploy these things. And once that is related to the digital twin, it is coined for the visual representation of the any physical system. So like this is the real supply chain, but I model it into the visual software. So where I can access all the things before implementing the projects to calculate the cost, emissions, what things I am getting, or I also conduct the emission and economic analysis of this supply chain.
As I can see, you already thought of and covered all of the crucial and important points because, as we know, many projects look viable on paper, but then collapse when transport and variability are factored in, what you've just mentioned.
Yes, yes.
Now, maybe let's talk about techno-economic assessment versus real markets. In your work, techno-economic assessments often assume ideal conditions, right? So,
Yes.
where real-world constraints most commonly break those models? Is it, let's say, fuel variability, downtime, or financing?
Uh, what I observed from the techno-economic analysis, the many people generally focus on the aspects what they are getting into the news and the published studies or the experts. But if they go into the reality, they need to check the various aspects. Like biomass is not free at all. You need to pay some amount of money to collect and transport it to your plant. So that is a major factor. Generally, people are considering the biomass is free. And once the biomass procurement cost increase by 10 to 20%, if we do the sensitivity analysis, the whole matrix will change. So generally, we measures there are various economic parameter, but if you are taking account the actualization of money, that means you are taking account the escalation rate, doing discount rate. So you will you might find that most people do not com- uh, comply these types of things into the economic assessment. That's why they are uh, whatever they are predicting is much more difference what in the reality. So in my study, I tried to incorporate all the factors like inflation rate from Reserve Bank of India, and also there are some constant like in the Canadas there are various provenance, and they have the different taxes and other things. So I tried to incorporate the state-wise. First, I accumulate the state-wise data and float it over the throughout the whole lifetime of the projects. Like I am creating the cash flows for the each year with their respective escalation rate. Like operational cost will escalate with different rate, labor cost will escalate with different rate throughout the plant. And these data you need to gather from the previous past reports. Once you have all
What is oh, sorry, yes, go on.
uh, so once you have the all the revenue and expenses stream, then you will discount those cash flows into to access the present value. After that, you have the various performance indicator like net present value, discounted payback period, also the internal rate of return. These things, along with the life cycle cost of electricity in terms of energy. So basically, these things, if we understand it, so life cost of electricity is the unit electricity of energy throughout its lifetime. And for the net present value, it's a discounted flow for the future cash flows. And for the payback period, it help you to decide in how much time you are getting your investment back. An internal rate of return where your net present value becomes zero. These are the some economic parameter we generally use to predict the economic financial visibility. If NPV is more than zero, then the project is economical.
So, what is the biggest? Because I was just about to ask you a few times. What is the biggest portion of cost associated with obtaining biomass? Is it transport?
It can vary from region to region. Suppose uh, in our study, biomass procurement cost is the one of the driving factor. But in some region, if you have the transportation distance more than 50 kilometer, or that eventually come transportation cost as a dominant cost.
And you said also it depends on the region. Are there regions that, for example, transport is on the second place and something else takes the reign, is the most expensive part of this biomass? Do you have any examples?
Yes, when we actually right now we don't need have any storage options for the storing the biomass. If we take example of coal, so we need to store the coal first, then we have to use it within the 26 days. Otherwise, it will degrade over the period of time. That thing, that is the same thing happens with the biomass as well. So I also calculated the dry matter loss. So it was coming around, I will lose around 16 to 24% of biomass if I store the biomass for 1 year.
Got it. So transport and storage, main factors. And now let's switch and talk about carbon credits, ESG, and green financing. Bioenergy projects are increasingly tied to carbon credits, as we know, and to ESG frameworks as well. From your perspective, where do these mechanisms help? And also, where do they distort incentives?
So carbon credits means either we are reducing, avoiding, or removing 1 ton of CO2 emissions from the atmosphere. So that is termed as the carbon credit. So we are seeing that the various industries are emitting a lot of CO2 emission. That's why the CO2 concentration in the atmosphere have been rise from 0.03% to 0.05% in the recent days. And we have the Paris Agreement, like we have to keep temperature level below the 1.5 degrees Celsius. Otherwise, the whole ice will melt down and the whole earth will flow with the water. So that was the major reason that drives the carbon credit mechanism. If you are polluting the environment, you have to pay some cost. So here the carbon credits comes into the picture. So many companies are currently buying the carbon credit to compensate or offset their pollutions that they are giving to the atmosphere. So there are various type of mechanism to calculate carbon credit, but as per my experience, I have seen carbon credits for the removing the atmosphere, removing CO2 from the atmosphere, either by the carbon capturing technologies or carbon sequestration, or they are avoiding the emissions. Suppose I am disposing waste into the landfill, it will create some emissions, but I diverted that waste into the energy, so I saved some emissions. That is also is there. And also, if I am collecting the fire prone forest residues from the forest and converting it to the energy, also it is saving the avoided emissions coming from the wildfire. The three have the different price. Each carbon credit has the different price that is defined by its source. Either it is avoided, either it is replaced, or either it is removed the CO2 from the atmosphere. So that things covers the carbon credit. So generally, if I am employing any type of renewable energy product, so it will give me some carbon credits. Right now, we have the carbon credits trading systems where the companies will buy the carbon credits from us. If we have the carbon more than carbon credit that we are emitting, so we can also sell them in the future. So this type of mechanism is currently coming around. Also, if we see, around 17% of the total emissions are comes under the carbon credit right now. So 83% are still we need to cover with these carbon credit or other type of technologies. And once we move to the ESG part, so it's a report card of any industry that represents how they are treating environment, how they are treating their employee, and how they are having the compliance with the local bodies standard international or national protocols. So that is something ESG. So they each environment, social and governance have different type of standards, like ISO 14040 for ESG, ISO 26000 for social, and there are various type of codes. So you have to measure these type of things. That's why various industries have been commissioned to cut down their emission intensity. They have target like 1 by third by this year, 1 by fifth by this year, and be completely by net zero. So net zero is something generally misunderstood. It is like whatever the emissions we are creating or leaving to the atmosphere, that should be completely offset by the various technologies. That is termed as the net zero. Green financing, basically, these are the funds which are solely dedicated to the installing of the renewable energy related systems into the world. So these are the funds generally utilized to fund them at low interest rate.
Thank you very much for those insights. I think this connects engineering reality with financial and regulatory systems, which will be pretty helpful for our audience. And now let's talk about internal combustion engines again. You work also with internal combustion engines in the context of alternative fuels. So if you could tell us, how do you see these technologies fitting into a realistic energy transition? And let's say, especially in emerging economies like India.
So we cannot ignore the transition phase. Right now we are right now we have to transit from the fossil fuels to the renewable energy. But in this transition era, we cannot completely rely on the new technology, because right now we are not aware that are the economic feasible or environmental feasible. And if the technology doesn't come into my pocket, then I will not buy it. For taking the example of electric vehicles, so they have some different concept, because some people are saying that electric vehicles are completely produce they are free from the pollution. But if we talk about their source, if the electricity is coming from the fossil fuels, how can we say that the whatever the electricity we are using to recharge our vehicle are the really pollution free? Also, they will create the emissions during their manufacturing process because we are extracting the semiconductors, then making these type of batteries. Similarly, we cannot completely rely on the internal combustion engine. Right now, the internal combustions have a lower economic value as compared to the electric vehicles and any other new technologies. So, in the developing countries, the per capita income is very low. So, if we suppose I am getting a car in 10 lakh rupees, which is completely based on the internal combustion engine. But if I go for the same level of car for the electric vehicle, it will cost me around 28 lakhs, just double. So right
Mhm.
now, I can say that the hybrid model are successful for right now because the fossil fuel prices are also the escalating. But in the future, we can see how the figures can grow or decline. But internal combustion right now, we cannot ignore those aspects because old the defense industries are totally rely on it. Like they are utilizing the military vehicles and many other things. Do we enough resources to create a completely renewable energy stream? Right now, my answer is no, but in the future, I am very optimistic we will have.
I'm usually very optimistic too. And now, maybe a piece of practical advice what practitioners should get right first. So, for developers, let's say municipalities or companies considering biomass or waste to energy today, if you could tell us what are the first three things they should do right before committing capital.
So we need to think about all the technologies simultaneously because we don't know which technology will turn out to be economical and economic viable or environmental viable and social viable. So once we start any research or any developing any market, we cannot say it will be a completely successful story. For example, the solar energy, once it uh, in 2002 it was introduced in the India. So, on that time, the cost was coming around the INR 15 rupees per unit of electricity, but it come down to the 1.50 rupees in the per unit of electricity in the area. But there were various programs to promote that solar energy function. However, currently waste to energy technologies and biomass energy gain recent attention due to their carbon credit benefits and other compliance. But I cannot say right now what thing might be best. We need to check the problem with their origin. Like for the waste to energy, we need to think about the where this waste is generating, what is its source, where the waste is generating. So we have to segregate the waste first, otherwise the supply chain become the more complex, and it will add up the cost and emission as well. For each problem, we need to think in the various angle and optimize that system. Then we will see how the things will work in the future.
Once again, thank you very much for this takeaway for our audience. As we are coming to the end of our conversation today, is there anything else we didn't touch on that you think is important to add or share with our audience?
So, as a researcher, I want to say don't think a research from a single lens. Also, I would like to say industry people or the government people, please invest more money on these type of research. And also, we have to work where the value of depth that is called the technology readiness level 4 to the technology readiness level 6. That is very important aspect where the developed technology in the lab can come into the picture from the industry perspective. So in this valley of death, we need to fight together like government, researchers, local people, industry, and other stakeholders hand to hand. After that, we would have a very reliable technology. So I would say to all, please focus and view all the lenses for the research.
And are you getting any focus at the moment from investors, let's say, outside India? Or for now, you're operating locally?
Uh, I have some connection from the abroad as well, but whatever whenever I indulge with them, I am more interested from the research part first. Then I try to incorporate their concern and their problem as well, so that the researchers and investor can go hand in hand.
Got it. Ankush, this has been a very grounded and useful discussion. What I appreciate is how clearly your work shows that sustainability outcomes depend on context, assumptions, and execution, not just labels. So, thanks for joining us today and for helping cut through some of the simplifications that dominate the bioenergy conversation.
Thank you, Carol. I also enjoy a lot during our podcast, and thank you once again for giving me this opportunity to share insights about the biomass energy and other aspects.
Thank you so much.